Okay, in this recording, we're going to be looking at the momentum worksheet. Now, momentum is, okay, we're going to start off with a couple true or false. So this one's kind of like a double negative. If momentum is not equal to the mass of an object divided by its velocity. And that's true, because momentum is equal to mass times the velocity. Momentum of an object can change. That's true, because again, if the object changes its velocity, it'll change its momentum. Number 3, though, is false. Two objects with the same mass will always have the same momentum. That's not true at all, because they could be traveling different velocities. All moving objects don't have momentum. That's false, because if they're moving, they have a momentum. Object speeds up, it gains momentum. Yep, just look ahead at the formula. P is equal to m times v, so if you increase the velocity, it has to increase momentum. Objects with different masses can't have the same momentum. Well, that's false, because if their velocity, if we have small mass or large velocity, you could have the same momentum as a large mass to small velocity. Direction does not matter. Now, this is patently false. False, because momentum is a vector quantity. It is a vector, so direction matters when it comes to momentum, so that's false. Momentum can be transferred from one object to another. That is true. During a collision, momentum from one can go to the other. Now, number 9, when objects collide, some momentum is lost. In the absence of outside forces, which is what we will deal with, this is false. Okay, we have a law of conservation momentum, which we'll talk about later, loco P, very similar to loco E, but law of conservation momentum. So we will, in the absence of outside forces, no momentum is lost. A tiny bullet can have more momentum than a huge truck, and that is true. Yep, again, it's all dependent on velocity as well. All right, so looking at number 11, a moving car has momentum. If it moves twice as fast as momentum, well, it's going to have to be 2 times as much, because P is equal to m times v. And so a lot of the easiest way to do these things is just to make up numbers. So if we say, hey, let's let our mass, I'm going to change colors here, let's the mass be 1 and the velocity be 1. If we multiply those, that'll give us a momentum of 1. Then, if it moves twice as fast, we'll change that to blue, the mass stays the same. So that stays at 1, but now our velocity goes to 2. That will give us a momentum of 2. So it's going to have to go 2 times. Now, at number 12, 2 cars, one twice as heavy as the other, move down the hill at the same speed. Compared to the lighter momentum, or lighter the car, the momentum of the heavier car, and this is also going to be 2 times as much. Okay, because in this case, this one has double the mass compared to the velocity. Now, given this following data, we're going to solve for momentum using P is equal to m times v. Just for the record, I don't like this formula. I don't like the way they did this. This should not be a capital P. This should be a lowercase p. We've already dealt with a capital P. That was power. So we'll make sure that you're using a lowercase p for this. So if they look, we did the first one for us. We have a mass of 0.04, velocity of 19, and momentum is going to be 0.76. Now, in each one of these, I'm going to be doing mass times velocity. So it's going to be a repetitive. But in this case, we'll take the 100 kilograms times the 10 meters per second, and that'll give us a nice 1,000 kilogram meters per second. And I'm not going to write that down because it's already up here in the top of this column. Skiers have a mass of 60, a velocity of 20. This will give us a momentum of 1,200. So our skier can have more momentum than a football player. Our bullet, with a mass of 0.004, has a velocity of 600. This will have a momentum of 2.4 kilogram meters per second. The frog, with a mass of 0.9 times the velocity of 12, will give us a 17. That's going to be 10.9 kilogram meters per second. A meteorite with a mass of 0.1, traveling a velocity of 1,000, gives us a momentum of 100 kilogram meters per second. The baseball, 0.14 times the velocity of 30, will give us a momentum of 4.2 kilogram meters per second. A wagon with a mass of 2 and a velocity of 3 will give us a momentum of 6. And finally, a satellite with a mass of 3,000 kilograms and a velocity of 8,000 meters per second will give us 2.4 times 10 to the 7th kilogram meters per second, or 24 million kilogram meters per second. Okay, going on to the next one, we have some sample problems. Again, in this case, we're looking for momentum. We're given the mass to be 2 kilograms, and so this is just another way of doing guess. And we have a velocity is equal to 2.8 meters per second. So if I'm looking for momentum, P is equal to m times v. And so P equals m times v. So momentum is equal to 2 kilograms times the 2.8 meters per second. And so my momentum is going to be a whopping 5.6 kilogram meters per second. We look at number 23. We have a marble that's rolling at a velocity of 1.5, momentum of 0.1. What's its mass? We're looking for mass. We're given a velocity of 1.5 meters per second and a momentum of equal to 0.1 kilogram meters per second. The relationship is still is equal to P is equal to M times V, but what they're trying to get here is if you're trying to find the mass, you could solve this, and I'll put it in orange, that the mass is equal to P over V. Now, I won't force you to do this. This is something we kind of do to an AP. You still can just use your same way where you go P is equal to M times V, and you have your momentum is 0.1 kilogram meters per second, and your velocity is, looking for the mass, velocity is 1.5 meters per second. And so you divide them through, and it'll give you a mass of 0.067 kilograms, so relatively small. But if you wanted to do it this way, this is, oops, sorry, let me do that again. If you wanted to do it this way, it makes it easier because you're doing the algebra ahead, just on the algebraic, or on the letters, and then you don't have to worry about losing a number here or there. Now, if we look at 24, April 15th, Cruiser loses on Titanic after running the iceberg. What was the cruise liner speeds? We're looking for the velocity. That's my question mark. And we know the mass. That's 4.23 times 10 to the 8th kilograms. And we have a momentum of 4.9 times 10 to the 9th kilogram meters per second. Now, our relationships here, again, P is equal to M times V, or if you want to get fancy, I'll put it in orange, V is equal to P over M. And this one I'll do the fancy way. So our velocity is equal to the 4.23 times 10, 4.9, my fault, 4.9 times 10 to the 9th kilogram meters per second. And I'm going to divide that by the mass of 4.23 times 10 to the 8th kilograms. And that'll give us a velocity of about 11.6 meters per second. And finally, number 25, suppose you're traveling in a bus at highway speed on a nice summer day, momentum of an unlucky bug is suddenly changed and it splatters on the front window. Compared to the force acts on the bug, how much force acts on the bus? We know that that's got to be the same. And this is from Newton's third law of motion. Okay, for every action or force, there's an equal and opposite reaction of force. Now, although the momentum of the bus is very large compared to the momentum of the bug, the change of momentum of the bus compared to the change of momentum of the bug, that one will also be the same. And this comes from the law of conservation of momentum, that the total momentum before has to equal total momentum after. So we'll have a little bit of a change of momentum there. Now, which experiences greater acceleration? Think of Newton's second law. Quick reminder, Newton's second law says that acceleration is force divided by the mass. Now, although the force is the same, because the bug is going to have a much smaller mass, it will have a much higher acceleration. So it's got to be the bug. And therefore, which suffers the greater damage? Obviously, it's got to be the bug. So hope that helps, and have a great night. We'll see you later. Bye.